Multiplication principle says that if you've got a series of decisions to make, like decision 1, decision 2, decision 3, and so on, and there are so many ways to make decision 1, so many ways to make decision 2, so many ways to make decision 3, and so on, that if you multiply these numbers of ways together, that will tell you the number of ways to make all the decisions. Let's write it down and read it. So if there are n sub 1 ways to make a decision 1, n sub 2 ways to make a decision 2. Now look, the subscript, n stands for the number of ways. The subscript just is a name for, okay, the number of ways for the first decision, right, decision 1. The 2 is just a name for decision 2, right? Just keeps track of which one's which, just a label. There's n3 ways to make decision 3, ... and then there's n, k could be some number, like, there's 20 decisions to make, k could be 20. All right, so how many ways can you make all the decisions? All you do is multiply these together. Just multiply them together, that'll give you a number of ways to make all the decisions. Here's an example. Suppose we've got 4 wires, red, green, blue, and yellow, and they need to be attached to a circuit board. So a robotic device will attach the wires. The wires can be attached in any order, and the production manager wishes to determine which order would be fastest for the robot to use. All right, use the multiplication rule of counting to determine the number of possible sequences of assembly that must be tested. Hint, okay, there are 4 choices for the first while, 3 for the second. Well, I guess we've kind of got the hint, tells us what exactly what to do already. We've got 4 decisions to make, right? Where the first wire is going to go, where the second, where the third, where the fourth. All right, so for the first decision, there's 4 wires, 4 ways to connect those. Right? Choose any one of those 4 colors. The second decision, well, there's only 3 wires left, so there's 3 ways to make that decision. Choose one of those 3 colors. For the third decision, there's only 2 wires left, and for the fourth decision, there's only 1 wire left. So there's going to be a total of 4 times 3 times 2 times 1. That's 12 times 2 is 24 ways to make all these assemblies. Let's do another example. In this case, Barbara is a research biologist for green carpet lawns. Right, so she's studying the effects of fertilizer type, temperature, at time of application, and water treatment. So she's studying 3 things, right? Fertilizer type, temperature at the time of application, and water treatment after application. She has 4 fertilizers. Okay, I'm going to write this down. Okay, so as far as fertilizers, there are 4. Where are we? There's 3 temperature zones. All right, so for temperature, there's 3 temperature zones, and then what else have we got? There's 3 water treatments. So water treatments, there's 3. All right, here's the question. Determine the number of different lawn plots she needs in order to test each fertilizer type, temperature range, and water. All right, so we've got 3 decisions to make. Which fertilizer are we going to use? Which water treatment, or which temperature, and which water treatment? So there's 4 ways to make the first decision, 3 ways to make the second decision, 3 ways to make the third decision. So that turns out to be 12 times 3 is 36 different, 36 different plots she has to make in order to test all 3 types. Here's another example. How many license plates could be stamped if each plate has to have exactly 3 letters and 4 numbers? All right, so look what we have to have. This license plate, like for Pennsylvania, has what? 3 letters and 4 numbers. All right, so I see a sequence of decisions. We've got 1, 2, 3 letters, and then we have 1, 2, 3, 4 numbers. So all in all, I've got 1, 2, 3, 4, 5, 6, 7 decisions to make. Right? For the first decision, what's the first letter going to be? The second decision, what's the second letter going to be? And the third decision, what's the third letter going to be? And then the fourth decision, what's the first number going to be? And so on. All right, so how many ways do we have to make this first decision? Well, it's got to be a letter. So there are 26 letters. Second decision, that's also a letter. Third decision, also a letter. Fourth decision. Now, the fourth decision, this is a number. So what numbers do you think we can use? I'm thinking we could use, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10. I think we have 10 choices here, and the rest of them are numbers. So this is going to be 26 cubed times 10 to the fourth. And my TI-84 says, that's probably an okay way to leave it, but this says 175,650,000 different license plates. Here's another example. What if we did this? What if the letters have to be unique? Well, let's say letters and numbers, right? So no repetitions. You can't have the same letters and you can't have the same numbers. So it's still got 7 decisions. 1, 2, 3, 4, 5, 6, 7. Now the first decision, I can choose any of the 26 letters. But for the second decision, I've only got 25 choices left, right? Because this decision here, this letter, cannot match this one. So whatever I use for the first one, I have to toss it out because I don't want any repeats. So then there's only 25 letters left for the second, and then I have to take those 2 out, 24. All right, so there's the letters. Now, digits. I can start with any of the 10 digits. But then I've already used that one, so there's only 9 left here to choose from. Right now I've used 2, so I have to toss those out, 8, and then 7. All right, so I'm going to multiply these together. That's using the multiplication principle. And now it looks like on my calculator, this says 78,624,000. So 78,624,000 unique plates like that. So another example here, a PIN code, something we're all familiar with. So it says a PIN code for a bank ATM is a 4-digit number. So determine the following. So first of all, how many PIN codes are possible? All right, so you got 4 digits. So this will be, I'll call it part A. So for part A, what are we going to have? I got 4 decisions to make. What do I want to use for the first number, second, third, and fourth numbers? Well, there's 10 digits I can use for the first, for the second, for the third, and for the fourth. Right, so what do we get out of here? Right, we get 10,000 different PIN codes. And the second one, how many PIN codes are possible if no repetition of digits is allowed? All right, so we just can't repeat the digits. So 1, 2, 3, 4. I still got 10 choices for this one. But then I can't use that one for the next digit. So how about 9? Then I can't use either of those, so there's only 8 left, and then 7. Okay, so this turns out to be, now if I multiply these together, I'm getting 5040. And this last one, oh, you know what, that's getting a little bit crazy. Let's not do that. Okay, so I'm not going to do this last one. I think we've got it up to now, and this is good enough for what we need to do. So there's another quick one. How many 8-digit passwords are possible? So we've got 8 decisions to make, right? 1, 2, 3, 4, 5, 6, 7, 8. Now, what are we going to do here if the passwords have to be just from the English letters? Okay, just from letters only. No numbers, no special characters. So if we just use letters, could be 26. Now, you can have repetitions. So 26, 26. All of these are going to be 26s. So what I get is 26 to the 8th. And that comes out to, let me look at my calculator, it's a 208, 827, 064, 064, and then a 576. Okay, so what is this here? This turns out to be, all right, here's millions, billions, 208 billion, 208 billion, 827 million, and so on. All right, it's a lot of possibilities. And then what if we added just one more? All right, so we've got these. what if we added just one more letter? So instead of an 8-unit digit, make it a 9-digit. All right, so how many are possible here? So this is going to be, well, it's going to be what? 1, 2, 3, 4, 5, 6, 7, 8, and then 9. All right, so that's going to be another 26, and we already know what that number is, right? That's this number up here. So now we're going to have 26 times this number here. All right, now I tried that on my calculator, and it doesn't come out nicely. It comes out like this. 5.4295036, and then 679, and then there's an E12. Now here's what that E means. This is just scientific notation. So it means this. There's 5.429503679 times 10 to the 12th. All right, so we're going to make an estimate here. This is a decimal point right here. Now, to get it into scientific form, we move the decimal to the left. To get it out of scientific form, we're going to move it to the right 12 places. So this is going to be 5, and then what have we got here? Count these places. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know what those other numbers are, so I'm just going to make them zeros. So it's going to be 4, 2, 9, 5, 0, 3, 6, 7, 9. How many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. This is going to be an approximation now. All right, so what is this? This is thousands, millions, trillions. Okay, so it's about 5.4 trillion. So if you have an 8-digit password, what's the probability, right? The probability of guessing a password, right? The probability of just guessing a password, if you just guess for 8 digits, well, there's this many passwords, right? There are what? 208 827 064 576, one of which works. Then the probability of guessing a 9-digit password, okay, that's going to be 1, because there's one password, over this 5442903 679. Okay, so this is about 1 out of 2 billion. This top one is about 1 out of 2 billion. Add one more letter, and it's 1 out of about 5.5 trillion.